All right, so let's begin the program. So the first speaker of the program is Professor Andrei Vesnin. He is a professor at the Sobolev Institute of Mathematics and also the director of the Regional Center of Mathematics at Tom State University. He is also a member of the Russian Academy of Sciences and a well-known expert in three manifolds, hyperbolic, particularly three-dimensional hyperbolic manifolds, knot theory, both classical, virtual. And he also has interest in recently chemical sciences, I think, application of knot theory in chemical sciences. So I welcome Professor Andrei Vesnin.
Thank you very much. So thank you very much for the invitation. It is my pleasure to give a lecture here in this workshop Notes Through Web. And thanks for hospitality of ICTS. I hope we will meet sooner or later in Bangalore and discuss our topics directly. As you know, knot theory has very many aspects, and today I'm going to discuss mostly geometric approach to study knots and links, and I will tell you something about the special class of free manifolds and links, which are called tetrahedral. Of course, you can imagine that there are some relation with tetrahedra, but this relation with tetrahedron hyperbolic three-dimensional space. So let us start. So this is the outline of my talk, and as you see, firstly, I want to recall you something about hyperbolic three-dimensional space. And after that, something about many special class of manifolds which are cusped. And then we introduce class of tetrahedral manifolds and discuss the census of tetrahedral manifolds. And after that, we discuss tetrahedral links in three-dimensional space. And finally, we discuss one of very important invariants, which is a volume. And we relate this volume with some classical arithmetic functions and give some expressions how you can calculate volumes from some arithmetic knowledge. And before choosing the topic, I thought about the direction which can be interesting for young researchers, as I suppose in this direction you can find very many interesting intersections with geometry, algebra, and computer science, and I would like to try to demonstrate it to you. So let us start, and I would like to recall you what means hyperbolic three-dimensional space and three-dimensional manifold. Of course, I hope you already know it, but just recall something. So we can consider a few models of hyperbolic three-dimensional space. Usually in Russia we call it Lobachevsky space because of Nikolai Ivanovich Lobachevsky, who introduced it, is one of the first in the world. And you can think about the model in the upper half space. So you consider x, y, t, the free coordinates, and assume that t is positive. And for the metric, use the form quadratic form. So this is dx square plus dy square plus dt square divided by dt square. And since you have this form, you can calculate everything about the geometry of this space. And in particular, if you're interested in geodesics, so it's easy to prove that geodesics in this space are just Euclidean half-lines or semicircles which are orthogonal to the basic plane t equals 0. And if you're interested in two-dimensional subspace, which are totally geodesic, if you're interested in planes, so in this case, planes are just Euclidean half-planes and semispheres, which are orthogonal to the plane t equals 0. So you can easily imagine how it looks. And since we are in geometry, we're interested in volume, and the element of volume can be easily found from the element of length. So, d volume is just dx divided dt divided by t cubed. So if you want to calculate something, you can do it using this formula. And now we can discuss action of some group in this space. And we can consider the boundary of our space, which is called absolute, which is just the Riemann sphere. And from the university classes, you can remember that the group of linear fraction transformations is one of the main important group acting in Riemann sphere. So we go this way, we consider the extension from the Riemann sphere to hyperbolic space, and usually it's called Poincare extension. So we do the following. We can consider the point in the hyperbolic space with coordinates x, y, t, and we consider this point as a quaternion, the given form. So x plus y I just a complex number, and we have tj is along one of quaternion coordinates, and the last coordinate is equal to 0. So if you have linear fraction transformation with the complex a, b, c, d, with normalization ad minus bc equal to 1, so you can extend this action as a action on quaternions. So to the point in our hyperbolic three-dimensional space, we correspond, we present it as a quaternion, and we correspond the quaternion in the following form. We take a z plus tj plus b, and we can see the product by inverse of c z plus tj plus d. So we have action of quaternions. After that, we'll get quaternion of the same form as we started. So the last coordinate will be 0, and the coordinate of j will be positive. So it belongs to as a point, it belongs to hyperbolic three-dimensional space, and have such an action. And of course, this Poincare extension have an actual geometrical meaning, but maybe I skip this part because I just want to recall something. So we see that a group of linear fraction transformation can be extended, and we will get so each action can be extended. You will get action in hyperbolic space, and we can state as a theorem that the group of addition isometries of hyperbolic three-dimensional space just isomorphic to PSL to C. And this isomorphism just to explain it on this slide. So we know what was the action, and you can see the group action acting in our space. So after that, we can consider the quotient space by this action and consider the quotient space with the hyperbolic geometry. So let me recall some definitions. Suppose we have n-dimensional manifolds. So very often we can introduce a geometric structure on this manifold. And we say that we have a hyperbolic geometric structure on manifold when we have a Riemann metric of constant sectional curvature -1. So this is the same as you consider hyperbolic space, and you consider the group acting without a fixed point and discrete, or acting properly continuous, and you consider the quotient space. It will be give hyperbolic structure. And of course, we consider not just hyperbolic structure, but we consider complete structures. And we say structure is complete if the induced metric is complete in natural sense. Why hyperbolic structure is so interesting in context of three-dimensional topology and in context of knot theory? One of the reasons is the so-called most of process rigidity theorem, and it says the following: if you have orientable n-dimensional manifolds with n starting with 3, and if you know that this manifold admits a complete hyperbolic structure of finite volume, then the structure is unique. So the structure is very rigid in this sense. It is unique, and if you consider hyperbolic manifold or just topological manifolds which can be occupied with hyperbolic structure, you can use this geometric structure to construct invariants. Because of rigidity theorem, these invariants will be topological invariants too. So it's there is many reasons to study hyperbolic structures, and since we're interested in nodes, so if you consider link node or link in three-dimensional sphere, we say that it's hyperbolic if its complement. The complement, of course, is three-dimensional manifold, and we say the node is hyperbolic if the complement admits a complete hyperbolic structure of finite volume. And it's natural to ask how many does there exist such nodes, or how many of them. And due to Thorson theorem, we can say that in some sense most of nodes are hyperbolic, or more exactly, if you have a prime node in three-dimensional sphere, so it is hyperbolic, either torus or either satellite. So for torus nodes we have classification, and the satellite is a from a very interesting special class, but the remaining many nodes are hyperbolic, and it's nice that we have hyperbolic structure, since this structure is unique, so you can use hyperbolic geometry to understand something about nodes, and in particular to construct their invariants. And we'll start with simple objects. So we have a space, and first of all we consider the tetrahedra in this space, and also in this case of polyhedra, we have a kind of rigidity theorem which was proved by Andrei in the 70s, and he proved that acute angle tetrahedra in hyperbolic free space is uniquely determined by these diagonal angles. So it's completely different from Euclidean situation, and you have rigidity, so everything in hyperbolic space is determined by combinatorial structure and diagonal angles. So we already fixed combinatorial structure, so everything determined by angles. And among all tetrahedra, we consider the class of ideal, such tetrahedra that all vertices belong to the absolute. And here you see a picture. So this picture presents tetrahedra. We have three vertices which belong to the Euclidean plane. The three vertices line on the plane, and you see the Euclidean triangle as a base. And the fourth vertex is on the top. It go to the infinity in Euclidean space. So another vertex go to absolute. And if you go, if you look at the neighborhood of this infinity vertex, you will see a Euclidean triangle. So this triangle is bounded by four faces. Three of them are vertical high Euclidean half space, and the fourth is just the part of semi-sphere based on 3 points on the Euclidean plane. And this is a typical Euclidean tetrahedron, and as a tetrahedron it has 6 diagonal angles, and the simple lemma states that opposite diagonal angles are equal. So the notation alpha 1, alpha 2, and alpha 3, and so opposite diagonal angles the same, alpha 1, alpha 2, and alpha 3. And moreover, since we have Euclidean geometry on the base, so we have Euclidean properties, so alpha 1 plus alpha 2 plus alpha 3 is equal to pi. And we use the notation T, alpha 1, alpha 2, alpha 3. So any ideal tetrahedron in hyperbolic free space is determined by these 3 angles, and sum of them is pi, so it depends just on 2 real parameters. And since tetrahedra will be our basic object, I want to say something about the calculations of its volume. So traditionally in hyperbolic geometry, volumes of polyhedra and volumes of manifolds are presented as expressions of so-called Lobachevsky function. And you can see this function, lambda theta. So this lambda, because of rational letter L, the first letter in the family name of Lobachevsky, is kind of d-logarithm, and you see this periodic function, and you have some maxima and minimal points which can be found. So the graph presented in the picture. So this function was called by Lobachevsky function in the paper written by John Miller, and the original Lobachevsky used a little bit different function, but very close to this one. And this function is very interesting. It satisfies very interesting Humbert identity. So you can calculate function with multiplied arguments. So suppose you have some integer m times theta, so you can calculate Lobachevsky function as a linear combination of Lobachevsky function in other points. And geometrical meaning of Lobachevsky function is the following. So if you consider tetrahedron with diagonal angles alpha, pi over 2, and pi over 2 minus alpha, so its volume is exactly 1/2 of Lobachevsky function calculated in point alpha. So here, infinity means that these two vertices belong to the boundary of hyperbolic space, belong to the absolute, belong to the Riemann sphere. So point go to infinity. And if you use a Lobachevsky function, then you can find a volume of any ideal tetrahedron hyperbolic space in a simple form. The formula was proved by John Miller in 1982. So if you have ideal tetrahedron hyperbolic free space with diagonal angles alpha, beta, and gamma, so other three diagonal angles are the same as we proved in the previous lemma, then volume can be calculated as a linear combination of three Lobachevsky functions calculated in point alpha, beta, and gamma. So it looks very simple formula, but only for the case of ideal tetrahedron. And the tetrahedron in which we will be interested in today is a regular ideal tetrahedron. So ideal means that all vertices belong to absolute, and regular means all the ideal angles are the same, so it's pi over 3. And from Milnor's theorem, we get a corollary that a regular ideal tetrahedron has the maximal volume among all tetrahedron in three-dimensional space, and this volume is given by three Lobachevsky function calculated in pi over 3, and here I presented the value. So it's some number which we can calculate as far as it's want. So I think that it was calculated up to 50 digits after the point. So it's approximately 1.01, something like that. So it's kind of constant, and you know how it looks. It's very useful constant in context of hyperbolic geometry. So we started with the tetrahedra, and we know how to calculate geometry of them, and we know about existence. So for any three angles alpha, beta, gamma, such that the sum of them are equal to pi, there exists a corresponding ideal tetrahedron. And now we can construct a more complicated object. We can construct a hyperbolic free manifold, and we will do it from a tetrahedron. So let us suppose that M is a connected hyperbolic free manifold. So manifold with complete geometric structure, hyperbolic structure, obtained by gluing together a finite set of provided joint ideal tetrahedra which belong to hyperbolic three-dimensional space. So we take this finite set, and we start to glue them. So for this set P, we consider set S, which is set of all faces of tetrahedra from our collection, and assume that they split in pairs, and we glue these along the faces, and we let us know this parent theta. So for the collection of ideal tetrahedra, you can see the collection of their faces, and we pair faces by some isometries of hyperbolic space. And so we have pairing theta, and of course this pairing extends to a pairing of ideal vertices of tetrahedra. And so we split all ideal vertices in classes of equivalent under this pairing. And for an ideal vertex we denote by in brackets this equivalence class. And after gluing, we'll get a manifold. So a class of equivalent ideal vertices is called a cusp of manifold. So such manifolds are called cusped manifolds. And if you look at cusp, we can try to understand what happens in our construction. So if you have V in the ideal vertex of some tetrahedra, so we can choose a horosphere, so sphere around the vertex, which intersect only those faces of our collection which are incident to V. And we can introduce a link of a vertex, which is just intersection of a concrete tetrahedra with this horosphere. And this horosphere give us Euclidean geometry. This link is a compact Euclidean polygon, and the pairing give us the gluing of such polygons, and this gluing will be along the similarities because by Euclidean similarities, and after that we will get some surface, and this surface correspond to ideal vertex, and it's called a link of the cusp. The cusp is just class of this equivalence class of this vertex, and we consider isometries, and if any isometry is orientation preserving, then we will get a surface which is Euclidean and oriented, so this is the torus. And otherwise, it can be a Klein bottle. So we'll get such construction. So you'll get a cusped manifold, and the links are tori or Klein bottles. And as you mentioned, the very important case when a Riemann geometric structure is complete. So it can be shown that hyperbolic three-dimensional manifold is complete if and only if for which its cusp, the corresponding link is complete. But now we mean a Euclidean surface in this sense. So cusped manifolds is quite wide the family, and what we are interested in to understand structure of them or some invariants of them, and one of nice parameters is complexity of cusped manifold. And this complexity determined it in terms of triangulation. So suppose we have three-dimensional manifolds, and we say that its complexity equal k if this manifold is means an ideal triangulation with chi tetrahedra, but the smaller number of tetrahedra is not enough. So k is the minimal number of tetrahedra enough to construct our manifold. So if the complexity of our manifold is equal to k, then of course we can bound the volume of this manifold. So Vk here, this is the volume of regular ideal tetrahedra. This is the biggest one. So in the class of all tetrahedra in the space. So you can estimate complexity is at least the rate of volume of our manifold and volume of regular ideal tetrahedra. And of course, if you fix number of tetrahedra, you'll get only finite number of manifolds. So for given complexity, only finite number of manifolds. So the natural problem to classify, the natural approach to classify three-dimensional manifolds, three-dimensional manifolds, is just to try to classify them according to their complexity. And the same, of course, for hyperbolic nodes. We can try to classify them according to their complexity. So according to minimal number of tetrahedra needed to construct them. And I want you to give you some example. This is very famous class of two-bridge nodes and links. So each of them is determined by rational number P over Q. And for this P over Q, you can see the continuous fraction. And you, depending on odd or even number of elements in this fraction, you will get diagram of one of two types presented here. And usually it's called the convex normal form of the bridge node. And here Ij denotes just a number of twists in direction depending on the sign of Aj. So this is two-bridge node, and we can estimate complexity of the complement of two-bridge node. So the bound is the following. It was our joint result with Carlo Petronio. So we found the low bound. So if you have a two-bridge node, you consider its complement. This gives you a three-dimensional manifold, which is for any determined by P over Q. So this complexity is always bounded by 2n minus 2. So this is lower bound, and fortunately the upper bound can be done in particular case. So Ishikawa and Nemota considered the upper bound for the general case. So it's presented in the next formula. And we see that the upper bound and lower bound consigned if you consider a particular case when parameters of your continuous fraction are just 2, sequence of 1s, and again 2. In this case, we know the complexity. So if you consider two-bridge node of given type, so its complement is the three-dimensional sphere can be obtained from 2n minus 2 ideal tetrahedron. This is the minimal number. So now let me go to the class of manifolds which are really interested. So it's called tetrahedral manifolds. So suppose we have a cusped hyperbolic manifold. So it's called tetrahedra. It can be decomposed into regular ideal tetrahedra. So biggest ideal tetrahedra which you can get in hyperbolic space. And this class is interesting also from the point of complexity, because if we use it K regular ideal tetrahedra to construct a manifold M, then complexity is exactly K. So we don't have a problem to calculate complexity, but question how to construct such a manifold. And for small k, examples are very famous. For example, if k will equal 1, there is only one tetrahedral manifolds, and it is known as the Giesecke manifolds. This example constructed by John Giesecke in 1912. This is a hyperbolic free manifold, but it is not orientable. It's obtained from gluing sides of one copy of tetrahedra. If you take k equal 2, so you use 2 regular ideal tetrahedra. In some sense, you have more freedom because you have 4 faces for one, another 4 faces for another one, so more possibilities to glue a manifold. And these manifolds, one of these manifolds is also famous. This is a figure 8 knot complement. And let me tell you a little bit more about it. So this is a picture of the figure 8 knot, and you can take 2 tetrahedra, regular ideal tetrahedra, and with the suitable gluing, you'll get a complement of this knot. And let me put 2 tetrahedra one on another one. Consider P, just union of 2 tetrahedra, where I have A, B, C, D, and a B, C, D to regular ideal tetrahedra. So all vertices of them belong to absolute of the space, and all diagonal angles are pi free. And let us consider the pairing of faces by isometries as given on the slide. So you have gluing F, gluing G, and gluing H, and this gluing identifies corresponding pairs of triangle faces. And this is exactly the pairing theta, which is considered in the definition. So there are three isometries which identify faces of union of two tetrahedra. And after that, we can check what happens with vertices. So, and of course, with edges. So firstly, look at edges. So we have edges of this polyhedra, which is union of two tetrahedra, and they split in classes of equivalent under the group action. So you see that BA equivalent to EA and equivalent to CD and to ES, so BD, and again go back to BA. And all these equivalents given by isometries from our pairing. So we have arrows with marked isometries. So firstly G, next F inverse, H, G inverse, and F, which give us a relation for the fundamental group. And another class of equivalence H's presented in the second line. So AD is equivalent to AC, equivalent to BE, equivalent to BC, and equivalent to AD, and is realized by isometries G, H, H inverse, and F inverse and H inverse. It's given another relation for the fundamental group. So the group will be generated by three isometries, and with these two kind of relations. And to check the complete structure, we consider equivalence of vertices. I recall we have union of two tetrahedra, and this union have 5 ideal vertices, which we know by the A, B, C, D, E, and all of them are equivalent to 1. And under the action of our group, we get the following sequence of gluing. So A, this is a vertex which correspond to a union of two tetrahedra. So there are 4 edges along which incident to this vertex. So we have foregone. So foregone which related to vertex A. We will glue it with foregone which related to the vertex B. Then with the triangle corresponding to vertex E, again foregone for vertex C, foregone for the triangle for vertex D, and finally we arrive to vertex to foregone to vertex A. And now what we have, these triangles and these foregones are constructed from regular triangles on Euclidean plane with angles pi over 2, pi over 3, pi over 3, and pi over 3. So just usual Euclidean triangles, and we can see that picture on the Euclidean plane, which is universal cover for our link, looks like this one, and this gluing can be realized by Euclidean isometries. So the cusp is complete. So hyperbolic structure on the figure not complement is also complete. And it gives us example of tetrahedral manifold. And of course, after that, you can ask about other examples, or ask how many are tetrahedral manifolds, and also which of them are not or link complements. And it's usual in hyperbolic geometry. Then people try to use computers and different computer programs, and many calculations were done by different group of peoples. And for example, Callahan, Hildebrandt, and Jeffrey Weeks, they listed all hyperbolic free manifolds which can be glued from at most 7 ideal tetrahedra, not necessarily regular, but just ideal. And there are more than 4,000 of such manifolds. And more than this list, it listed all hyperbolic free manifolds which can be glued from 8 ideal tetrahedra, and there are more than 12,000 of such manifolds. And jointly with my colleagues Evgeny Fomenych and Vladimir Tarkaev, we consider the situation of gluing of regular ideal tetrahedra. And independently of previous examples, we constructed all tetrahedral manifolds of complexity at most 8. So glue it from at most 8 ideal tetrahedra. And they were recognized by homology groups and Torah invariants. And up to this number 8, we can do everything by hand, but after that it became more complicated. And we also found tetrahedral manifold of complexity 9 and complexity 10. But for 10, we get a bad news that not all manifolds can be recognized or distinguished by first homology group or by Torah invariants. So we decided to use another technique, mostly based on computer software. And now just may tell you something about the most useful computer software for hyperbolic geometry. And now we have three basic computer programs. Maybe the most famous of them is SNAPy. It's a computer program for studying topology and geometry of manifolds, and mostly focuses on hyperbolic geometry. And as you see from abstract of Abhijit Champanerkar, he will tell you more about hyperbolic geometry and also about SNAPy. Another program is Regina. It was a project started by Benjamin Barton, and this software very good to work with triangulations and normal surfaces and angle structures. And this third computer program is called it Recognizer. It was written by Sergei Matveyev and Vladimir Tarkaev, and it focuses mostly on complexity of three-dimensional manifolds. So for big number of tetrahedra and for big manifolds, of course, it's more useful to use computer software. And the main result which I want to present to you here is just the result about classification of tetrahedral manifolds. This is a joint result by Evgeny Fomenych and Sauros Garthvalidis and Matthias Göner and Vladimir Tarkaev and myself. It was published in 2016 in journal Experimental Mathematics. And really, there are many experimentals in computer in software. So you can find paper in the journal, and also you can find this paper in archive. This is our archive reference. And if you go to archive, then you can find a lot of files attached to this preprint. And there are 62 files which contains all the computer programs which we wrote or use it, and also data files which you can use for computer programs SNAPy and Regina which present our manifolds. So the theorem is the following. So there are the number of combinatorial tetrahedral tessellations and tetrahedral manifolds up to 25 tetrahedra in Orientable case and up to 21 tetrahedra in non-Orientable case, listed in the table below, and table show us number of tessellations and number of manifolds. So you can see sometimes there are no good tessellations. For example, for free tetrahedra, we don't have orientable tessellations with free tetrahedra, but there is one non-orientable. And for example, in the case of 11, there are also no orientable tessellations. So this is the total number of tessellations, number of gluing of given number of regular ideal tetrahedra, and the next two columns is number of manifolds, because of course you can imagine that different tessellations can be used for the same manifold, so sometimes tessellation give you the same manifold. And the last column is about homology link, which we discussed a little bit later. So this is the result of computations by the software presented in our Hive, and everyone can take our data files and use these files to work with our manifolds using Snappy or using Regina software. And in this construction, the most hard computational part was combinatorial enumeration of tetrahedral triangulations. And after that, there are many manipulations to check in gluing. And it was quite hard calculation. For example, for both cases, for Orientable case and non-Orientable case, we use it Xeon processor, and calculations take it about 6 weeks in each case. That's huge of information. And we presented our results in the following form. So to each tessellation, we corresponded signature, and you can see that name of manifolds or tessellation is orientable, tetrahedral. 2 means you use only two tetrahedra, and we start numeration from 0, 0, 0. So up to 7 tetrahedra, you have tessellations and with signatures presented here. And there are some special kind of dehydration representation, which maybe I need to go to details. So taking this signature, you can easily reconstruct tessellation as a manifold. So we use notation with the numbers and letters just to use 64 version of the dehydration. So we use these numbers from 0 to 63 with the correspondence to this whole correspondence to letters, big letters, and numbers and symbols. So we have such signature, and after that we can describe manifolds, and after that we check it if there are really complete hyperbolic structure in this construction. And this construction is very special. This is obtained from a regular ideal tetrahedra, and due to Colin McLaughlin and Alarik, we can observe that all these examples are arithmetic manifolds, and you can see the diagram of coverings. So the different tessellations cover different tessellations, and you can see on the left all examples of tetrahedral. On the right, there are one example, we call it M208. This notation from Snappy. It's arithmetic, but not tetrahedral, but commensurable with that one. So now go to tetrahedral links. So some of our manifolds are link complements, and we introduced a notation of homology link complement. We say that our manifold is homology link complement if its homology group is the same as the group of link. So its condition is equivalent to the fact that our manifold M is the complement of a link which belong to integer homology sphere. So we checked all our manifolds and found those of them which homology link complement. And in this table, you can see how many homology links for a given number of tetrahedra. For example, if you have only 2 tetrahedra, there are only 1 homology link, which is exactly a figure 8 knot. And for 4 tetrahedra, there are two links. One of them is called Berger link, and one 2-component link with 6 crossings, and so on. For a small number of tetrahedra, you get link with not a big number of crossings, so the classified, so we present the notation of this link. And as you can see, in all cases, only even number of tetrahedra is used. So you have a conjecture, which, of course, theoretical conjecture, but we see that true for small number of tetrahedra. The conjecture is that every tetrahedral link complement has an even number of tetrahedra. And now I'm going to present you some nodes and links. And this is the list of nodes. There are only one node, the figure 8 node. All other objects are links. And the complement of them can be decomposed in a finite number of regular ideal tetrahedra. For example, from 2 tetrahedra, you get a figure 8 node complement. Here, from 8 tetrahedra, you can get this 2 link. Next example will show which kind of link complements you can obtain using 8 tetrahedra, and so on. For 10, you can picture like this one, and also for 10 and sometimes for 12, you have another links. So all of them are interesting from geometric point of view because complement of these links are hyperbolic manifolds, and they can be decomposed in finite number of regular ideal tetrahedra. And there are more examples for 12. You can see maybe this last one. This is a link. This non-accelerating link with 13 crossings, and this number of this link in the list is 8,382. And this enumeration is related to some interesting equation or some concept introduced by Colin Adams and Sherman. So, denoted by sigma k, the minimum number of ideal tetrahedra which are necessary to construct the identical hyperbolic free manifold with k cusps. So for small values, sigma k is known, and there's some conjecture. In general case, conjecture is for sigma k with k at most 2 have the upper bound for k minus 4. So for 6, 7, and 9, we have conjecture like this one. And similarly, we can define sigma rk, the minimum number of regular ideal tetrahedra which necessary to construct a rentable hyperbolic free manifolds with k cusp. So from our examples, we get values of this parameter for small number of tetrahedra, like presented in the last 2 lines. And finally, maybe in a few minutes, I would like to relate volumes of tetrahedral manifolds with the classical arithmetic functions, so with the classical topics started from beginning of 20th century, from Bianchi, Humbert, and other the famous mathematicians. So let's consider tetrahedral manifolds. I mentioned already. Any of them is constrained with a figure 8 node complement. So if interested in the volume of the manifold, so we can take half of the complexity, multiply volume of the figure 8 node complement. And figure 8 node is very much studied object, and we know the group, the metal group of the complement is generated by 2 elements with just one relation, and we know that it has a faithful representation in PCL2C, and to the first generator we correspond to matrix of such type, and for the second element we correspond to matrix just 1101, and omega here just an element of the form -1/2 plus square root of -3 divided by 2. So this group, fundamental group of the figure 8 node, just subgroup of PCL2 of the rational extended by root from -3.
We don't have the information also, sir.
And we can consider the general situation, and let us denote by F the imaginary quadratic number field corresponding to parameter D. So we take extension of Q by the square root from minus D. And let us denote.
Sir, from today onwards, the conference which I am organizing is actually going on.
So let us denote by OD the ring of integers. And the PC2 with all this ring of integers is classical object. This is a discrete subgroup of PCL2C, and all such group are known as the Bianchi group. The Luigi Bianchi studied this group in the beginning of 20th century. And from that time, it is known that the quotient of hyperbolic space by such a group is a hyperbolic obifold. And of course, if you have torsion-free subgroup, so subgroup with element of finite order, then the quotient will be hyperbolic free manifold. And arbitrarily observed that fundamental group of the figure naught is just a subgroup of index 12 in this Bianchi group. So if you want to find volume of the figure naught, you can interest in volumes of obifold corresponding to Bianchi group, and just multiply or divide by 12. So let us go to the classical stuff, and recall with the Dedekind zeta function. You can define it as a series of given types. We will consider the ring of integers and the sum taken over all non-zero prime ideals, and I just corresponding norm. And the classical result by Humbert, obtained it in 1990, you can find volume of the quotient of hyperbolic space by Bianchi group, the following form. We just take a German D, and you calculate, and you times is to Dedekind the zeta function. So this expression maybe looks a little bit different, but it's very nice in the context which discussed below. And for example, in our case, we consider it quadratic imaginary field correspond to D equal 3. So you have a Dedekind function corresponding to -3, and let's recall the Dirichlet L function is defined as such a series where he n is just directed character, and we calculate it for our value -3. So we can substitute it here, and so we see how our L function looks. It's just a series of given form, and you can recall the classical relation between he function and zeta function and L function. And since we know the value of zeta function in point 2, just pi squared divided by 6, we obtain the volume of the Bianchi obifold as expression like a product some constant times L function. And since the volume of the figure complement is 12 times bigger, we'll get a formula for the volume of the figure 8 not complement. It's just 3 square by from 3 divided by 2 L function in 2, and here is parameter -3. And there is also one more interesting relation with the classical stuff. So if you consider polynomial depending on k variables or complex numbers, so there is known object call it Mahler measure. You can take just a log of this polynomial and integrate over product of circles. This is a big M P, and also you can consider the logarithm of this expression denoted by smaller m. And if you take just one variable, for your polynomial, and if you present your polynomial as a product of x minus roots of this polynomial, then this Mahler measure just the product of high coefficient, model of high coefficient, and products of models of roots which lie outside of unit disk. And this Mahler measure is very interesting stuff in approximation of functions. Also, there is very famous conjecture formulated by Lehmer in 1933. He conjectured that there is some lambda, constant lambda, such that if we have a monic polynomial, then its Mahler measure equal 1, or at least this constant lambda. And as I know, this is still open problem, and the best known value for lambda is just 1.7 and so on. As this is the root of the Lehmer polynomial of degree 10 presented here on the slide. And this polynomial is very interesting. It has two real roots, one outside the unit disk, one inside the unit disk, and all other roots belong to the unique circle. And also this polynomial is interesting because it's in context of knot theory, it's just the Alexander polynomial of a pretzel minus 2, 3, 7 knot. So if you consider two variables, also there are some results how you can reduce the case of two variables to case of one variable. And also a very nice relation proved by Smith. If you consider the logarithmic Mahler measure of polynomial 1 plus x plus y, so it's up to constant. It's exactly the L function which we already discussed. So from our previous discussion in the relation between volume and L function, we can obtain that the volume of the figure is not complement just 2 pi times logarithmic Mahler measure of the polynomial 1 plus x plus y. And it looks a little bit surprising, but there is very nice motivation for this result. And this motivation, homogeneous case, can be described as the following. So let us consider polynomial depending of x and y, depending of x and y, and such that is equal to a plus bx plus cy. And we have three parameters, a, b, c, and consider Euclidean triangle with side lengths equal to a, b, and c. We assume they are positive, or you can take models. And we have these triangles, and for this triangle we have some angles, alpha, beta, gamma, such that sum of them equal to pi. And for these three angles, which give us pi in the sum, we can consider the ideal hyperbolic tetrahedron with such diagonal angles. And there is a very nice theorem proved by Malloy in 2000. So suppose A, B, C are complex numbers, and such that there exists a Euclidean triangle with lengths equal to modulus of these three complex numbers. And let us consider alpha, beta, gamma be triangles with this Euclidean triangle. And let us denote by Z the model of ratio A to B and times exponent in degree I gamma, where gamma is one of angle which has is opposite sides with adjacent sides A and B. Then the following formula holds. So if you consider the pi times logarithmic Mahler measure of this a plus bx plus cy, then we get volume of the tetrahedra plus some expressions in logarithms of length and times some angle of this triangle. And in the case if such triangle doesn't exist, then Mahler measure just a logarithm of maximum of length. And here Tz means that ideal triangle with the diagonal angles related to complex number z. So the three angles are the following argument z. and argument 1 divided y minus z, and argument y minus 1 divided z. So it's easy to check that for any z, sum of these angles of these three angles equal to pi. So you have ideal tetrahedral in hyperbolic space with with angles corresponding to complex number, and in particular case, when a, b, and c equal to 1, we'll get just a regular triangle on Euclidean plane with angles pi over 3, pi over 3, and pi over 3, and corresponding tetrahedral just a regular ideal tetrahedral. So in the particular case of this theorem, we get just considered example, and it's very nice that volume of a figure not complement can be expressed as a Mahler measure of such type. So it's a very nice expression. Okay, and finally, I just want to give you some reference. So for the main theorem in this talk, you can use a reference to our paper published in Experimental Mathematics in 2016. And if you're interested in more information, then all files with all programs and computations results are available supplementary files to the archive preprint. Also, they can be found in the Madeti journal homepage, presented with number 3. And the last 3, reference number 4, 5, and 6, is reference to some computer software, which we use it inside the proof of the theorems. So the first one of them is Snappy, the second is Regina, and the third one is Humbert program. This is a Python model for verification and computation for hyperbolic free manifolds. And you can find all of them according to the reference in the web. Okay, so thank you very much. Please, questions if you have.
Any questions? Particularly from students? So well, if there are no questions, so let us thank Professor Andrei Vesnin for the wonderful talk. So I encourage students to go through the slides. I'm sure they will be available on the ICTS website. And at least you can experiment with the wonderful software that Professor Vesnin has mentioned. I'm sure students can experiment with that. Okay, so there seems some question. All right, it's just thanks. Okay. All right.
I have a question.
All right, yeah, please.
Yeah. So the thing you showed about the fundamental group of the complement of the figure 8 knot, where you realize that as the index 12 subgroup of PSL2 O3, is that something you would expect for general hyperbolic knots as well, or is that like we just get lucky with the figure 8 knot?
Okay, you can this situation of -3 is very specific. So this is kind of a particular case of arithmetic knots and things, and there is a very nice result proved by Alarin that there are only one arithmetic knot. This is exactly the figure 8 knot. So if you're interested in other examples, you discuss in links. And for other Bianchi group, the arithmetic links were listed, as I remember, in papers of Grunwald, for example. So there's some reference about other rings of integers too, of course.
Okay, thank you.
All right, so Andrei, there is one more question from Abhijit. So the question is, can you compare the complexity of a knot with some other classical invariants like crossing number, unknotting number, and so on?
In this case, complexity just a number of tetrahedra.
So for hyperbolic knot, yeah.
I think that it can be some correlation, but I don't think that somebody studied the real relation. It will be interesting to compare, of course.
I see. All right, so I don't see any more questions.
Maybe the last remark, I hope that in the forthcoming talk of GB Champanerkar, he will discuss more about hyperbolic nodes and links, and maybe he explain how to use Snapier program. We don't discuss with him, but I suppose our talk are connected in some sense.
Yeah, yeah. Okay, so one more, yeah, Andrei, one more question from the same participant. So given a tetrahedral hyperbolic 3 manifold, is there a way to know its whether it's a complement of a link? Interesting question.
Yes, we in our case you can see our computer programs, and you can go for details to the paper, and there's some explanation how we did it. It was done really by computer software. I mean, we tried with some drillings of fundamental domains, and after that, using Snapier, we compared with some invariants of least complements. So it's difficult to do by hand. You can find the computer program how we did it.
Yes.
Also, we use Snappy to distinguish and to recognize link complements. Because inside our proof, we have used canonical decomposition, and from canonical decomposition, we constructed manifolds, something like that. So I skipped many technical details, fortunately.
Limitation of time. Any more questions, particularly from students?
Another small question. So when you like you showed us some examples of tables of some 3 manifolds you have computed. In there, what does the signature of a 3 manifold represent?
Oh, yeah, the signature represented for here for small parameters. So this is the signature for triangulation. So you have a fixed number of tetrahedra, and firstly you describe how faces of one tetrahedra glued with faces to another of another tetrahedra. So it's a procedure was used by Jeffrey Weeks, and it's called dehydrated representation. So very short sequence of symbols which describe this gluing. And we use it 64 bytes and some special coding. And finally, we obtained coding, and from this coding, we went to minimal lexicographical sense, and signature has the following information. So the first letter just corresponds to number of tetrahedra. So you see C corresponds to 2, E corresponds to 4, and S corresponds to 5. So the first is just number, and after that you take the remaining symbols, and there is some algorithm how to go from this signature to a real gluing of tetrahedra. It's not easy to describe, but it's some rule which can be described. It's already described in some papers, for example, by Jeffrey Weeks, who introduced the dehydrated presentation.
Thank you.
Yeah. So Andrei,
so you can see it directly, but it's just some coding.
So there is
in
one
principle, it explains what you have 4 faces for the first tetrahedra, also 4 faces to the second, and so on, and it's described which faces of tetrahedra you glue.
I see.
Okay, so there is one more question from Vishak Narayanan. Is there a correlation between the number of link components and the number of cusp in the complement?
I think I tried to describe the relation. For example, here, so sigma k is just a minimum number of ideal tetrahedron needed to obtain free manifolds with k cusps. So there's some relation, and
Any more questions?
these results are mainly from particular examples.
So let us thank Professor Andrei Vesnin for this wonderful talk, which gave a panoramic view of this knot complements hyperbolic geometry. And it was really amazing. It connects with number theory. Thank you.
Thank you very much.